Okay, I'm done. Welcome again to this second lesson of the Analytical Techniques for Wave Phenomena PhD course. In the first lesson, we introduced some fundamentals about complex functions, analytic complex functions, or holomorphic complex functions of one variable. And in particular, we considered the definition of differentiation. Just a moment, maybe. There is another one, Umair. Okay. Good morning, Umair. Can you hear me?
Yes, Professor, I can hear you.
Okay, perfect. So I was saying that in the first lesson, we introduced the fundamentals about differentiation and also some concepts about the analytical functions as mappings from one complex plane to another one. What we will do today instead is to provide some fundamental information on integration in the complex domain. Now, integration is a basic process. In real analysis, there are many integration processes you may be acquainted with. For example, the elementary Riemann or Cauchy integration, which was then brought to perfection or completion by Lebesgue, and also many other names of mathematicians are related to complex integration, to real integration. In the complex plane, integration is not only important in itself, but mainly because it is an essential tool for the proof of many results that would be otherwise extremely complicated to prove without complex integration. As in the real case, actually, the name integral has two different meanings. They are related, of course. The first meaning is that of an indefinite integral, which means a function whose derivative equals a given function in a region. If we are talking about analytic functions, then we are thinking of the antiderivative of the analytic function. Whereas definite integrals, they are numbers, and the integration process for obtaining this number for a given function implies that you have defined an integration domain. We will deal with integrals defined along curves. So you draw a curve in the complex plane, and for simplicity, we will consider quite smooth curve. So a curve composed by a finite number of differentiable arcs. And so we will speak about piecewise differentiable arcs. This is our integration domain. And actually, the integration process that leads ultimately to the number, which is the result of the integral, is not restricted to analytic functions because it's sufficient that you have a continuous function for the process, the integration process, to converge. And actually, what we do integrating along a curve is the standard Riemann integration once you define a real parameter for your curve, as we will see in a moment. So this is the formal definition in the upper box of this slide of an integral, that's the standard integration sign, along a curve gamma, here below the integration sign, of a function f, which, as I said, is only required to be continuous, not necessarily analytic, with respect to the complex variable z. The meaning is of this expression at the left-hand side is provided by what you can find at the right-hand side. That this is a standard real integral along an interval that goes from a to b with respect to a parameter t, which is the parameter that describes your curve gamma. In fact, the curve gamma is represented by a parametric representation like z equals z of t, where z is the complex number, and t is the real parameter that goes from a to b. So if you let the parameter t vary from a to b, the point in the complex plane will describe your differentiable arc. And the definition implies that you integrate the function f multiplied by the first derivative of the parametric representation z prime of t. Why this definition? Well, it can readily prove that with this definition, what you obtain, so the number that you obtain, is not dependent on the specific parameterization of the given arc. And that's important because the very same curve in the complex plane could be represented in infinitely many ways, different one from another, by simply changing the parametric representation. For example, once you establish a one-to-one correspondence between the old parameter t and the new parameter tau through any smooth function phi, what you obtain is a new parametric representation, so you can indicate it with the symbol z tilde. So the complex variable z is equal to z tilde as a function of the new parameter tau, which is obtained by simply a function composition. That's the old parametric representation z composed with the new function phi that relates the two parameters. Now, also the limits for the new parameter will be in general different. So instead of going from a to b, we go from alpha to beta, where a is the image of alpha through the mapping phi, and b is the image of beta through the mapping phi. Okay, so if we do this change of parameter, what we need to do in the integral is to perform a standard change of variable in the integration, and this implies that the differential is transformed by introducing the derivative of the mapping function phi. So we have the function f that we are integrating, calculated as a function of z, which is a function of t, which is a function of tau. So this is ultimately a function of tau. Then there is the z prime that occurs in the definition of the integral above. And then there is the phi prime that pops up from the rule of changing variables from the differential. Now, look at those derivatives, z prime and phi prime, by the rule for differentiating a function of a function. What you get is nothing but the first derivative of the z tilde function as a function of tau. So you can more compactly write the second integral at the bottom. As you can see on the right, there is an integral from alpha to beta. Just a moment. Sure, of course. Please come. We have a new attender in presence. Okay. And so what you obtain is, at the bottom right of this slide, an expression in terms of the new parameter tau, which you can compare with the expression in the box above. That's exactly the same. So the form of this integral is exactly the same. So this means that the number that you obtain with this integration process does not depend on the way you chose to represent your piecewise differentiable arc. Okay? Let us give some elementary properties of this integral along an arc or a path. Sometimes we will talk about paths. First of all, let us define the integration along the opposite arc. So if instead of going from A to B, we go from B to A in the integration along T, this means that we just need to change the sign. So we obtain the same number, but with a different sign. So by convention, the integral along the opposite arc, so the same arc, but now we run in the opposite direction, gives you the same number, but with a difference in sign. Okay, and that's quite intuitive. Another useful property of the integral is its additivity. So look, for example, at the complex plane on the left. You see that our arc is made of three different pieces, gamma 1, gamma 2, and gamma 3. You obtain this by simply inserting some points which divide your arc. Now, the integral along the entire arc, so gamma 1 plus gamma 2 plus etc., up to gamma n, is by definition the sum of the integrals along the arcs. Well, actually, this is not a definition. This is a consequence of the definition of integral if the situation is as in the left complex plane. That's because of the additivity of the standard Riemann integral. Whereas this is actually a definition if the situation is like in the complex plane on the right, where, as you can see, we don't have a subdivision of an initial unique arc, but we have just the union of separated arcs. So in this case, we need to define the meaning of the integral along the sum of those arcs, and the meaning is provided you by the right-hand side. Okay, so in any case, the operation that you need to do is to perform the integral along each sub-arc, and then sum the results. Okay. Now, it's interesting also to explore the relation of this integral with respect to a different kind of integral, which is the integral with respect to the arc length. And to examine this, consider the absolute value of the integral we have discussed so far, here on the left. Now, as you know from elementary properties of the Riemann integral, the absolute value of an integral is less than or equal to the integral of the absolute value. So if you move the absolute value inside the integration sign, you get this inequality, where now you can see we are integrating the absolute value of f with respect, note, also we have inserted the absolute value around the differential, because that's a complex differential, which means, in real terms, that you integrate from a to b, that's a typo, that should be from a to b, the absolute value of the function f times the absolute value of z prime with respect to the real variable t. This can also be written in a more compact notation as the integral along the arc gamma of the absolute value of the function with respect to the arc length ds, because ds is the elementary length of the arc, which is nothing but the product of the absolute value of z prime times the differential with respect to t, the real parameter t. To give you an example, consider the exponential function e to jz. Okay. Now, if the arc we established for our integration is a portion of a circle, as you can see here in the plot, the arc gamma is a portion of a circle with a certain radius, capital R, and the parameter for this arc is simply the phi1 to phi2. And note that both phi1 and phi2 are strictly between 0, the angle 0, so the positive x-axis, and pi over 2, which means the positive y-axis or imaginary axis. Now, under these assumptions, look at the exponential function we are considering. Since the parametric representation of this arc is in the form of a second exponential, so we have the radius r, which has the meaning of an absolute value in this case, and there is the parameter phi, which has the meaning of an angle or the argument of the complex variable z. And if you insert this parametric representation inside your function, what you get is an exponential of an exponential. So e, the exponential of jr times another exponential of j phi. Now, if you consider the expansion of this second exponential using the Euler formulas, what you get is the splitting of this exponential into two parts. The first one is a real exponential, which is its absolute value, the exponential of minus r sine of phi. Then there is this second exponential whose exponent is purely imaginary, that gives you the argument. That's the exponential of j times r times the cosine of phi. So now let us see what happens to the absolute value of the integral of this exponential function along this arc. As we said, the absolute value of the integral is less than or equal to the integral of the absolute value. So instead of the exponential function, we now write only its absolute value inside the integration sign. And so you can see the exponential of minus r sine phi. Then there is the absolute value of the differential of the complex differential dz, which is the elementary arc length. So we can write this also as ds. Note that the sine function is decreasing when the angle phi goes from 0 to pi over, is increasing, sorry, when the angle phi goes from 0 to pi over 2. So if we now, instead of writing sine of phi, we write sine of phi 1, which is the smallest value among those that the variable phi can assume, then what you get, because of this minus sign, is a number which is greater than or equal to the original exponential. So if you do that, you can establish a further inequality in which now the exponential does not depend anymore on phi, which is the integration variable, so you can take it outside the integral, okay? And what you remain with is just the integration of the constant equal to 1 with respect to the arc length, which gives you the length of the arc. So the length of this portion of a circle, which is by elementary geometry equal to the product of the radius of the circle, r, times the difference of the angles phi 2 minus phi 1. Okay. Now this expression is interesting because you can see what happens now when you let the radius r go to infinity. If the radius r goes to infinity, the length of the arc, of course, goes to infinity, but it does so quite slowly because that's an infinite, a linear infinite. It goes to infinity linearly with respect to r. Whereas the exponential, the real exponential here in front of everything, goes to 0 much more strongly, as the exponential does when it goes to 0. So the product ultimately goes to 0, which means that in the limit when the arc has an infinite radius, you can neglect the value of this integral. Now, this is, I gave you all the details of this calculation because that's a quite standard thing that often occurs in many calculations in the complex plane. That is, what happens is that many times there are integration paths along curves that go to infinity, and often, not always, but often, the contribution of those curves, or better, the integral along those curves, goes to 0 when they recede to infinity. So you can neglect them in your calculation. But anyway, you have to show that this is true in any case you have in front of you for the specific problem at hand. And this example gives you a flavor of the kind of calculations that are needed to establish this. Okay, let's go on. We can see also the connection between given of the integration in the complex plane with something that you may be familiar with, that is the integral of real differential forms, which is nothing but the integration that you use in physics, for example, when you calculate, I don't know, the work done by a force. So in that case, you have a field of forces, for example, and that's the real differential form, and you perform the integration along a given path. That kind of integration is the integral of a real differential form, and you can obtain the connection by splitting the function you are integrating into its real and imaginary parts, so u and v, but also the same with the differential, so you have dx plus j dy. If you perform the algebra, you can now separate the complex integral into two parts, a real part, which is given by this integral here, the integral of u dx minus v dy, and that's the integral of a real differential form, plus j, and now we have the imaginary part, another integral of a real differential form, in this case the integral of v dx plus u dy. Here at the bottom of this slide, I recall you the definition of the integral of a real differential form in terms of a given parametric representation. So what you need to do is to evaluate the functions u and v through the parametric representation of the arc. So in place of x and y, you place their dependence on the parameter t. And in addition to that, in place of dx, you write x prime, so the first derivative of x with respect to the parameter, times the differential dt, and so on. That's the usual way you would calculate an integral like that. Why is it important to recognize that there is a connection with the integrals of real differential forms? Well, because there is a wealth of results in mathematical analysis about the latter kind of integrals. For example, you may recall this fundamental theorem about line integrals of differential forms The theorem is the one in the box. The line integral defined in a given region, an open set of the plane, of the differential form p dx plus q dy depends only on the endpoints of the curve gamma along which you are calculating this integral, if and only if there exists a function u, in this case a function of two real variables, x and y, defined in omega, with the property that the partial derivative of u with respect to x is equal to p, whereas the partial derivative of u with respect to y is equal to q. Of course, this is the well-known fact that if you have, in this case, a two-dimensional vector field, say v, whose components, whose Cartesian components are the functions p and q, then this vector field is conservative, so its line integral depends only on the endpoints, if and only if it admits a scalar potential, so a function u, a potential u, from which you can derive the vector field by means of the gradient operator, okay, gradient or del or nabla operator. So what we are stating in this theorem is the connection between the existence of a scalar potential and the independence of the integral on the path for given endpoints. Okay? Now, as you know from elementary physics, the independence of the integral from the endpoints is equivalent to saying that the integral is actually zero for any closed curve, as you will see in a moment. However, before going to that, if you apply this independence of the integral from the path for given endpoints to the complex integral we are discussing now, and if you split these into two parts, as you can see from here, so you let fz dz be equal to f of z dx plus j f of z dy, then this integral will depend only on the endpoints if and only if there exists a potential, let's call it capital F, such that its partial derivatives with respect to x and y are equal to, respectively, f and jf, which means exactly the same as writing that the partial derivative of capital F with respect to x is equal to minus j capital F, the derivative of capital F with respect to y. And that's easy to see that this is simply an alternative way of writing the Cauchy-Riemann equations. And since we know that the Cauchy-Riemann equations characterize an analytic function, what we have got is that the integral will depend only on the endpoint if and only if the function you are integrating is the derivative of an analytic function. So here analytic functions come into play. Okay, we started with a continuous function f. That's what we need to be able to calculate the integral. And we have discovered that this integral depends only on the endpoints if and only if this function f is the derivative of an analytic function, capital F. What we will discover in the course of this lesson is that under this condition, also the function f, lowercase f, is itself analytic, which is not something guaranteed from the beginning. Now, as I said, the independence of the integral on the path for given endpoints is equivalent to saying that the integral along any closed curve is equal to zero. That's another characterization of conservative vector fields, as you know. And as I said, we will see that if a function f is such that its integral along any closed path is equal to zero, that's an example of a closed path, then we will be able to prove that under this condition, the function f is itself analytic. Okay, so there is a strong connection between analyticity, which was defined in terms of differentiability, and integration. And so actually, this property, the fact that the integral along any closed curve is equal to zero, could be equally well assumed as a definition of analyticity. Okay, we could define analytic functions as those continuous functions which share the property of having a zero integral along any closed path. But we will see that in a few minutes. Just a moment, I need to drink. Okay, let us give some examples, very important examples actually, and let us consider monomials, which we know are examples of analytic functions. If you consider the monomial z minus a to n, where n is a relative integer different from -1, and a is a fixed point in the complex plane, then we may very easily prove that the integral of this monomial along any closed curve is equal to 0. Why? Well, because the monomial is the derivative of another monomial. That's the derivative of 1 divided by n plus 1. So you see why n must be different from -1, because otherwise this denominator would be equal to 0, times z minus a to n plus 1, and that's the elementary antiderivative of any monomial. But since this is a monomial in itself, it's analytic, so we have discovered that our integrand is the derivative of an analytic function. And so, as we said, it is guaranteed that the integral along any closed curve will be equal to 0. So you don't need to actually perform the calculation of this integral. You just need to recognize that the integrand is the derivative of an analytic function defined in a region which contains the path gamma, of course. This is understood. Now, it's interesting, however, to see what happens when n is equal to -1, because in that case, things are very different. In that case, what we will do is to actually perform the calculation. So we will consider as a curve a circle C of a certain radius, rho, and center at the point A, okay? This circle has the parametric representation z equal a plus rho times e to jt, where t is the angle. In this case, the parameter has the meaning of an angle that goes from 0 to 2 pi. And rho is, of course, the absolute value of this complex number, and that's the radius of the circle. What we will integrate is the function 1 divided by z minus a, which is z minus h up elevated to the power -1. Okay, let us see what happens. Imagine your differential dz. To evaluate this differential, you need to evaluate the first derivative of z with respect to the parameter t. So you need to differentiate this parametric representation. Now, in the differentiation, the constant a vanishes, whereas the exponential is the derivative of itself. However, the argument of the exponential contains the factor j, so there is a factor j that pops out. So z prime of is equal to j times rho times e to jt. That's the numerator of this fraction, whereas the denominator, z minus a, if you look at the parametric representation, is nothing but rho times e to jt, which is also present in the numerator, so you have a simplification, and what you get in the end is just the parameter j that popped out from the first derivative. So you need to integrate j with respect to t, where the parameter t goes from 0 to 2 pi. Of course, this is an elementary integral that is equal to 2 pi, so what you get is the quantity 2 pi times j, which is different from 0. So in this case, we have an example of an integral along a closed curve that is different from 0. This means that this function you are integrating, 1 divided by z minus a, is not the antiderivative of any analytic function defined inside the disk of center A and radius rho. Because otherwise, you would have that the integral would be equal to 0. But we have just calculated the integral, and the integral is different from 0. But since the antiderivative of the integrand is the function, the logarithm of z minus a, as you know from elementary calculus, we have obtained an important result. That is, it is impossible to define a single valued branch, analytic branch of the logarithm function with argument z minus a inside an annulus. So inside any annular region centered at the point A and going from an arbitrary radius ρ1 to an arbitrary radius ρ2. So that's impossible. And why is that impossible? If you remember, in the first lesson, we introduced the Riemann surface of the logarithm, and we saw that the origin, so when the argument of the logarithm is equal to 0, that's a branch point. In this case, we have a branch point at the point a, because when z is equal to a, the argument of the logarithm is equal to 0. And that branch point needs to be connected with infinity with some branch cut. So you should imagine that the complex plane is cut along a line that goes from a to infinity. And this prevents you from having a unique analytic branch of the logarithm. Okay. So it's impossible to have a logarithm that is continuous along an entire circle, because in any case, the circle would be intersected by the branch cut. Okay? Now, since we have seen an example of a function whose integral along a closed curve is different from 0, this is the good place to introduce an important concept, which is the concept of the index of a point with respect to a closed path. Here you see a theorem that says that if you have a closed path gamma contained in the complex plane, and you let omega be the complement of gamma, so the set of points which do not belong to gamma, and if you define this function of the complex variable z ind with subscript gamma of z, whose definition is given by the right-hand side. So you calculate the integral along gamma of zeta minus z, and you perform the integration with respect to the variable zeta, which is the Greek z. And finally, you divide the result by 2 pi j. Okay, if you perform this calculation, then this function of the variable z turns out to be integer valued. So the result you obtain is an integer number, which is not apparent from the definition, of course, because that's a complex integral divided by an imaginary quantity. But actually, this is what happens. And this integer valued function is constant in each component of omega. So you can imagine a closed curve generally divides the plane into different regions. For example, a circle would divide the plane into an interior region, a bounded region, and the outside, which is unbounded. This is true for any smooth closed curve as a consequence of a famous theorem by Jordan, the closed curve theorem of Jordan, which is absolutely not simple to prove. The theorem of Jordan says that any smooth closed curve divides the plane, the curve needs not to self-intersect with itself as a circle, for example. Well, any not self-intersecting closed curve divides the plane into exactly two regions, an unbounded one and a bounded one. That's a very elementary fact, whose rigorous proof required many efforts in topology. But in any case, the fact is that we have those regions, and the index, the function we are defining now, is an integer valued function that is constant in each of those regions, and in particular, it is equal to 0 in the unbounded component of omega, okay? So if you calculate the index of any complex number z when z is outside your curve in the unbounded component of omega, then what you obtain is 0. What's the meaning of this index, and why are we introducing it? Well, to give you some example, if you consider the point A1 in the complex plane and this specific closed curve that, as you see, goes around this point, then the index in this case would be equal to 1. Whereas if you consider the point A2, which is in the unbounded component of omega, of the complement of gamma, then in this case, the index would be equal to 0. And why in the first case the index is equal to 1? Well, because it can be shown that 2 pi times the index of any point A is equal to the net increase of the argument of the complex number z minus A, where z depends on the parameter t. So if you let the parameter vary, and so the point z describes entirely your curve, then the complex number z minus a, which you can imagine as a vector, which has a starting point at the fixed point a, and whose ending point is instead variable with the parameter t along the curve. Okay, well, this vector changes its orientation and its angle with respect to the positive x-axis, so varies. And in general, if you perform an entire tour around your closed curve, this angle will increase. So that's the net increase of the argument of this complex number. And if you divide this increase by 2 pi, so you obtain the index, what you obtain is the number of times your curve wins around A. That's why the index is also called in English winding number, in Italian numero di avvolgimento. Okay? So the geometric meaning of this index is very elementary. And that's why in this example you are observing the winding number of the index of the point A1 is equal to 1. That's because you perform a single tour around the point A1. Well, actually, this is not entirely apparent from this drawing, because in addition to the drawing, I should also specify the parametric representation, because it could well be that when the parameter goes from the initial value to the final value, the point describes, for example, the closed curve twice. That depends on the parametric representation. So that's not entirely evident from the drawing. I should also specify the parametric representation. But in any case, the index will be always an integer value that is different from 0 for interior points and is equal to 0 for exterior points. That's the important point to stress. Well, the index of the point enters in the formulation of the fundamental, of what is probably the most fundamental theorem of the entire subject of complex analysis, which is the so-called Koshi Theorem, which we'll now start to examine in its local form. In the second part of the lesson, we will also see its global form. This is the statement of the Koshi Theorem in its local form. The Koshi Theorem, as the name says, was first formulated by Cauchy. However, Cauchy assumed too many hypotheses. In particular, it assumed that the function f was analytic, whereas Goursat, another French mathematician at the end of the 19th century, was able to relax some of those assumptions. So in this formulation, you have a minimum number of assumptions. You have a convex open set omega, a point P inside this open set, a continuous function in omega, so we do not assume that the function is analytic. We just need its continuity in the entire omega, okay? But we assume that it is analytic in omega without this exceptional point, P, okay? Then f will be the derivative of some capital F, which is analytic in the entire omega. And therefore, as we know now, its integral along any closed path will be equal to 0. And that's true for any closed path gamma contained in omega. Note that this region, omega, in addition to being open, is also convex, and that's why this is a local version of the theorem. So this convexity assumption gives the local character to the theorem. We will be able to relax also this assumption, but we will do that the second part of this lesson. What we will see is that this assumption actually implies that the function f is holomorphic in the entire region omega. So the point P, let's call it an exceptional point because we did not assume analyticity at that point, is not really an exceptional point. However, this way of formulating the theorem is useful because it can be directly used to prove the so-called Cauchy integral formula, which you can see in this next slide, in which the index appears. What is the Cauchy integral formula? The Cauchy integral formula in a convex set is the following. Suppose gamma is a closed path, as you can see in the bottom slide as an example, which is described by some psi function of a parameter t, okay? And this curve is contained by assumption in some convex open set omega, so we are able to use the local version of the Koshi theorem. And furthermore, the function f is analytic or holomorphic in omega. Then if z is any point in omega, which does not belong to gamma, as in the example you can see at the bottom of this slide, where you can see the point z is in the interior of the curve, okay? Then what happens is that the function f at the point z times the index of z with respect to the curve gamma is equal to the right-hand side, which is 1 divided by 2 pi j times the integral of the function itself, f, now evaluated on xi, divided by xi minus z, and the integration is performed with respect to xi. Now let us stop for a moment to look at this formula to really try to understand it. Well, first of all, the left-hand side. In the left-hand side, you see there is the function f evaluated at the point z times the index. What we saw about the index is that if the point z is in the outside of gamma, so it's like this point A2 with respect to gamma, so it is located in the unbounded component of the complement of gamma, then the index is equal to 0. So in that case, the left-hand side of this equation is equal to 0. And so this tells us that the integral at the right-hand side will also be equal to 0, okay? So if you calculate the integral at the right-hand side of this formula for any point z which is outside the integration domain, so the curve gamma, what you obtain is 0, identically. That's the first result of this formula. But more interesting is what happens when z is instead, as in this picture, inside the curve. So the winding number or index is different from 0. And so the left-hand side gives you the function f up to a multiplicative factor, which is an integer. Okay. Now, in this case, what you get is a representation of the function f in a point z in the interior in terms of the values that the function f takes on the boundaries of the region whose boundary is the curve gamma. So this tells us that if you know an analytic function on the boundary of a domain, that's enough information for being able to recover the analytic function in any other point in the interior. So an analytic function is a very special object. If you know it on the boundary, then you know it everywhere inside the boundary of the domain. Okay, which is something not trivial at all if you consider a general function of two variables in the Cartesian plane. Okay. Now, in addition to being beautiful by itself, the Cauchy integral formula is an essential tool for proving an extraordinary number of consequences. The first fundamental consequence of this Cauchy integral formula is the result that any analytic or holomorphic function is representable by power series inside its domain of definition. Why is that? Well, consider an analytic function inside a given open set omega, which is in light blue here in the picture, and consider any point A inside this omega domain, and consider also a disk entirely contained inside omega, so with radius r, such that the disk in green is entirely within omega, okay? And consider what tells us the Cauchy integral formula about the value of the function f at any point z which is inside the green circle, as you can see, for example, here. Now, the Cauchy integral formula gives us a representation of the function f in terms of an integral which is performed around the boundary of the circle, okay? So this dashed line at the boundary between the green area and the blue area. However, the integrand can be manipulated a little bit. The integrand is the function f divided by xi minus z. Xi is the integration variable. Now, if you add and subtract the number a, which is the center of the disk in the denominator, and you factor out the term xi minus a, what you get in the end is the sum of a geometric series. So you can easily see that the factor 1 divided by xi minus z is equal to the sum of this geometric series, whose general term is z minus a to n divided by xi minus a to n plus 1. Okay. Why is that? Well, because this geometric series converges, and it does so uniformly on the boundary of the circle. That's because we are inside its circle of convergence. As we saw in the previous lesson, a geometric series converges in the complex plane inside the circle having center in the origin and radius equal to 1. If you consider any compact set inside this convergent circle, then you have that the convergence of the geometric series is absolute and uniform. Why is it important that the convergence is uniform? Because, as you may remember from calculus, if you have the integral of a series that converges uniformly, then you are allowed to switch the two operations, so you can take the series, the infinite summation, outside the integral, and you can integrate, therefore, term by term. Okay? If you do that, you obtain what is written at the bottom of this slide. You get a representation of the function f in terms of a series in which you see the red part is now a number. We can call it Cn. And we have the monomial z minus a to the nth power. So what we get is actually a power series representation of the function f, whose coefficients admit an integral representation that generalizes the Cauchy integral formula, because now, instead of having xi minus a, we have a power of this xi minus a that depends on the index n that goes from 0 to infinity. Okay? Why is this a fundamental result? Because we observed in the first lesson that if a function is representable by power series, then it admits an infinite number of derivatives. Each of those derivatives is also representable by a power series, and in addition, that power series is the Taylor series of its sum. So the coefficients of a power series are related to the derivatives of the sum. Okay, so what we have discovered is that if a function is analytic, then it is representable by power series, and as a consequence, its first derivative is also analytic, and so also the second derivative, the third derivatives. In short, an analytic function is characterized by having all the derivatives, and all of them are analytic functions. This is an exceptional result if you compare these with what happens with real functions of a real variable. It is very easy to conceive a function which is differentiable, but is not twice differentiable. You can imagine as many examples as you wish. Instead, in the complex plane, the assumption of differentiability, whose definition is the same as in the real case, as you may remind from the very first slide of the first lesson, then in the complex plane, the assumption of differentiability implies the differentiability, or better, the analyticity of all the derivatives of any order. Okay, so it's a very, very strong assumption. And we have almost for free another interesting consequence, which is called which is known as the Morena, a Spanish mathematician, which is in a sense a converse of the statement of the Koshi Theorem. The Koshi Theorem tells you that if a function is analytic, then its integral along any closed curve is equal to 0. Morena Theorem tells you the opposite. If you know that a continuous complex function in an open set is such that its integral along any closed path is equal to 0 for all closed curves, note that this must be true for any choice of a closed path, then you can conclude that the function is analytic.
The proof is actually extremely simple because the hypothesis, that is the fact that the integral along any closed path is equal to 0, implies, as we observed a few slides ago, that the function f, the integrand, which was assumed to be only continuous, is the derivative of an analytic function capital F. But now we know that analytic functions have analytic derivatives. So we can conclude that f is itself analytic. And that's the statement of Morena theorem. Okay? Okay, I think that this is a good moment for making a break. So I will stop for, say, 15 minutes. So we will be back at 11 and 10 minutes. If you have any question, of course, feel free to interrupt me and at any time. Okay, I hope this was clear so far. So see you in 15 minutes.
Okay, welcome back. I will. Sorry? Oh, no problem. We can let it. Okay. Let me enlarge again the screen. Okay. Before going on, I have to make two corrections. The first one, as Professor Frezza mentioned me, actually Morera was not Spanish, but he was Italian. Okay. And the other one is about the local Koshi theorem. To be precise, the formulation made by Cauchy was based on the assumption that the function f is analytic. However, Cauchy assumed in addition to that the first derivatives were continuous. In that case, it's very easy to show that the theorem is true based on the green formulas in the plane. However, the continuity of the first derivative is actually not needed in the proof, and Goursat discovered that with an entirely different proof, which does not make use of green formulas, and that is why we just need to assume analyticity, and actually analyticity with the exception of with the possible exception of a point, as in the formulation I showed you. Okay, having said that, we can go on. We are examining the consequences of the Cauchy local theorem. First of all, we showed that any analytic function is representable by power series. So a third possible definition of an analytic function could be that an analytic function is the sum of a power series in the complex plane. We have now three possible alternatives. We can define analytic functions in terms of differentiability, as we did, or we can define analytic functions in terms of representability as sums of power series. And finally, through Morena Theorem, we can define them in terms of integrals, as those functions whose integral along any closed curve is equal to 0. Okay. That's another important consequence of Cauchy formula. And we will now speak about the zeros of an analytic function. So let now omega be a non-empty open set, which will be assumed to be connected. Okay. Let f be a holomorphic function in omega, and let z of f, capital Z of f, be the set of points A belonging to omega where the function is equal to 0. So that's the locus of the zeros of the function. That's also called the zero set of f. Then there are two possibilities. Either the zero set coincides with omega, so the function is identically 0 in the entire omega region, or otherwise, if that's not the case, then the zero set has no limit point in omega, and in this latter case, to each point in the zero set, so to each zero of the function, there corresponds a unique positive integer, m, which is called the order of the zero, a, such that the function can be represented in omega as the product of the monomial z minus a to the mth power times a function g, which is analytic in the entire omega region, okay? With the property that g is different from 0 at the a is not a 0 of the function g, okay? And furthermore, the zero set could be infinite, but at most countable, okay? As I said, m is called the order of the 0, and as a consequence of this property, you have these interesting uniqueness theorems if you know that two functions are analytic in omega, and those functions coincide, so f and g, those two functions, are equal for all z in some set which has a limit point in omega, then this means that their difference is 0 in this set. However, if the zero set has a limit point in omega, then we must be in the first of the two possibilities, that is, the zero set coincides with the entire omega. So this means that the function f and g are actually equal everywhere. So if two analytic functions coincide in a set that has a limit point in omega, they are actually equal. So you have a uniqueness theorem. Okay. In other terms, if you know an analytic function in a countable set of points that has a limit point in omega, then there is
a unique analytic function that has those values, okay, in omega. Also, this kind of behavior is a very peculiar one, because if you remove the assumption of analyticity, then you can enforce the value of the function in a countable set of points, and this does not restrict you in any way the function at all the other points in your region omega. So again, analyticity is a very strong property. As another example of the power of the Koshi theorem, we will examine now the singularities, or better, the isolated singularities of an analytic function. The definition is the following one. If a point A belongs to omega and the function f is analytic in some open set omega without the point A, so the function f is analytic everywhere with the exception of the point A, which is therefore an interior point of omega, since omega by assumption is an open set, then we say that f has an isolated singularity at that point A. Now, a function, an analytic function can have different kinds of behaviors in a neighborhood of an isolated singularity. The simplest thing that may happen is the one examined in this slide, and that there is the possibility that the function can be defined also at the point A, so that the extended function f, that is now defined in all the region omega, is analytic in the entire region omega. If this can be done, then the singularity is said to be removable. Now, this actually occurs if and only if the function f is bounded in a neighborhood of the isolated singularity. So if it is bounded in a disk, we call it a punctured disk. So the disk without its center. So the locus of all points in the complex plane whose distance from the origin, actually whose distance from the point A in this case, is strictly between 0 and r. So they are the interior points of a disk with the exception of the center of the disk itself. Okay. Now, if the function f is bounded inside this region, then we may conclude that the singularity is removable, and the proof proceeds in a very simple terms. We can define a new function, an auxiliary function h, to be equal to 0 at the center of this disk, so h of a is equal to 0, whereas at any other point inside omega, it's equal to z minus a to the second power times the original function f. Now, the boundedness assumption of the function f implies that this auxiliary function h is actually differentiable everywhere. Well, in any point of omega, with the exception of a, this differentiability is a direct consequence of its definition as the product of a monomial, which is analytic, and of f, which is also analytic. The point a is to be treated differently. However, if you apply the definition of differentiability at the point A, so you perform the incremental ratio, you will see immediately that this incremental ratio tends to 0 because the function f is bounded. Now, since h is differentiable in the entire region omega, it is analytic in omega, so it admits a power series representation, which is this one, in which you have the coefficients Cn, and n now goes from 2 to infinity, because the first two coefficients must be equal to 0, because by construction, the function h has a 0 of order 2 at least, because of its definition. Okay, so we do not need the two first coefficients in this power series. The analytic extension of our function is obtained by setting the value of the function at the center of the disk be equal to C2, so the first of those infinite coefficients, and then shifting the coefficients by 2, so to define f as a sum of this power series, where n now goes from 0 to infinity, and the coefficient is now C sub n plus 2. Okay, so this is our analytic extension of a function in the neighborhood of a removable singularity. But this is the mildest behavior that we can expect. There are also other possibilities, as you can see in this theorem, that classifies the behavior of isolated singularities. So if we have a point A inside omega, and our function f is analytic in omega without the point A, there are three possibilities, mutually exclusive. The first one is the one we have considered in the previous slide. So F has a removable singularity at the point A, which is equivalent to saying that F is bounded in a neighborhood of this point. Otherwise, it is possible that there exist numbers, C1, C2, up to Cm, where m is a positive integer, and those numbers are different, and the last of those numbers is different from 0, so Cm is different from 0, such that if you evaluate the difference between the function f and this finite summation where k goes from 1 to m, and you see there is the coefficient c sub k divided by the monomial z minus a to the kth power. Okay, so that's a sum of rational functions, because the monomial is in the denominator. Okay, then in this second case, this difference has a removable singularity at the point A, so it can be extended to an analytic function. Okay, so we can see that in this case, our function f is equal to an analytic function plus this sum of rational functions that are inverses of monomials, and each of those monomials goes to 0 when z tends to a, so therefore the reciprocal goes to infinity. So basically the function f is unbounded in a neighborhood of the point A. But there is also a third possibility in which what is described in the second case does not happen, and the function has not a removable singularity. So the remaining case is a case in which the function has a very weird behavior in the neighborhood of the point A, because in this third possibility, it can be shown that for any positive radius r, that is the radius of a disk with center at the isolated singularity A, then the image of the disk without its center, of course, where the function would not be defined, well, the image of this disk is a set that is dense in the complex plane. What does this mean? This means that in any neighborhood of this isolated singularity, you can find a point whose image through the analytic function f goes as close as you wish to any point in the complex plane. You can go as close as you wish to any point in the complex plane in a neighborhood of these isolated singularities if we are in the third case. In the second case, we say that the analytic function has a pole singularity of order m, and this finite summation in which there are the inverses of the monomials is called the principal part. That's the singular part of the function. Okay. In the third case, we say that the function has an essential singularity at the point A, which is different, essentially different, I would say, from the behavior of a pole singularity. And it's useful to extend this classification of isolated singularities also to classify the behavior of functions at infinity. So infinity is what happens very far from the origin of the complex plane, but to make things more rigorous, it is possible to, for example, consider this stereographic projection. So imagine a sphere which is bisected by an infinite plane, which is the complex plane. And now you can establish a one-to-one correspondence between any point, the points of the complex plane, lowercase z, and points on this sphere, which you can think as a sphere of unit radius and center at the origin of the complex plane. The one-to-one correspondence is obtained by simply with a straight line the general point in the complex plane with the north pole of this sphere, the point N, section capital Z. Yes, please.
I was missing your audio for just a lapse of time.
Okay,
okay. Thank you. Perfect. Sorry for interrupting.
No problem. As you can see, you get a one-to-one correspondence in which the points in the northern hemisphere of the sphere corresponds to complex points in the plane which are located outside this unit circle. okay? Whereas points inside the unit circle, like z prime, they correspond to points on the southern hemisphere, okay? So the south pole would correspond to the origin of the complex plane. Now, the point is that the one-to-one correspondence is actually between the complex plane and not the entire sphere, but the sphere without its north pole, because as you can understand from geometry, there is no point in the complex plane that corresponds to the north pole. However, if you let the complex point z go to infinity, that is very far from the origin, you can imagine that its corresponding image, capital Z, on the sphere will go closer and closer to the North Pole. So it's useful to add to the complex plane a single additional point which cannot be drawn, and that's the point, the infinite of the complex plane, which would correspond in this stereographic projection exactly to the North Pole, okay? And we say that a neighborhood of this infinite point is the set of points whose distance from the origin is larger than a certain threshold, like this capital R number here, okay? Since a function is not defined at infinity, we can treat infinity as an isolated singularity. So we must examine the behavior of our analytic function in a neighborhood of infinity, and by convention we will classify this isolated singularity by letting the function f correspond to a function g by means of this inversion. We evaluate f at 1 over z, so points in a neighborhood of infinity get mapped by 1 over z to points in the neighborhood of the origin. So we can now, what we get is an analytic function g in a neighborhood of the origin, where the origin is an isolated singularity for this new function g. Now we can classify this isolated singularity. There are three cases. It can be a removable singularity, a pole singularity, or an essential singularity. And then we apply this classification to the function f. So we say that infinity is a removable singularity if the function f is bounded in its neighborhood, or the function f has a pole singularity at infinity, and in that case it has a behavior like a polynomial. Any polynomial has a pole at infinity whose order is equal to the order of the polynomial, as you can guess by replacing z with 1 over z and examining what happens to the resulting g function in the neighborhood of the origin. And finally, we can say that the function f has an essential singularity at infinity. For example, the exponential function, which is entire, so it's a function holomorphic in the whole complex plane, has an essential singularity at infinity, as you can guess from its behavior on the real and imaginary axis, because if you examine the behavior on the real axis, but also just on the real axis, you will discover that if you go to infinity along the negative real axis, the exponential function becomes a real exponential and goes to 0. But if you go on the opposite direction along the real axis, it goes to infinity exponentially. So in a neighborhood of the infinite point, your exponential function is neither bounded nor it goes to infinity like a power, because the exponential function goes to infinity faster than any finite power. So we don't have a removable singularity, and we don't have a pole. If you look at the behavior on the imaginary axis, there the exponential function is bounded in absolute value, so it cannot be a pole, because in the neighborhood of a pole singularity, the function is unbounded. So we must deduce that the exponential function must infinity, so a very complicated behavior in its neighborhood. Let us see some other important consequence of the representability in power series, the so-called Koshi estimates. It's useful to observe that any power series in the complex plane can be seen as a trigonometric series. Well, if you evaluate the power series on any circle of radius r, so if you let z be equal to a plus r times the exponential e to j theta, where theta is an angle that describes the circle, then what you get is this series where the coefficients Cn are multiplied times the radius r to the nth power, and this is a complex exponential, which is typical of the Fourier series in the complex domain, in the complex form. Okay. Now you can recover those coefficients of the power of the Fourier series from the theory of Fourier series by evaluating this real integral 1 divided by 2 pi times the integral from minus pi to plus pi of the function f evaluated along the circle times the reciprocal of the exponential e to j n theta, so e to minus j n theta, with respect to theta. Those are the Fourier coefficients. And you also have all the results known from the Fourier theory, for example, Parseval formula. So if you evaluate the infinite summation of the squared absolute values of the Fourier coefficients, the sum of this series, which is convergent, is equal to 1 divided 2 pi times the integral from minus pi to plus pi of the absolute value squared of the function where the integration is made with respect to theta. Okay. Now, since, however, the coefficients of our power series are, since any power series is a Taylor series, are related to the derivatives of the function f evaluated at the center of the circle, so at the point 8, then if a function is isomorphic in a disk, and if we know that the function f is bounded inside this disk, so its absolute value is never larger than some constant, say capital M, then by this fact we can conclude that the absolute value of the partial derivative of the derivative of order n of the function f evaluated at the center of the disk is bounded above by this quantity n factorial times m, which is the bound, the upper bound for our function, divided by the radius of the disk up to the nth power. Now, as a consequence of this, you have a classical and powerful theorem by Liouville, which says very simply that every bounded entire function must be a constant. So if you know that a function is analytic everywhere in the complex plane, and in addition, this function is bounded, then this function must be a constant. So a very trivial example of a function. The proof is immediate. If we know that the function f is bounded by some constant m for all z, then what we said about the Parseval theorem holds for any circle of any radius r. So in this case, you can estimate the integral in the Parseval relation with the constant m squared, because the function f in absolute value is never larger than m. So you can replace the absolute value of the function f with its upper bound, m, and you take it outside the integral, and then the integral is equal to 2 pi, so you get m squared. But this is possible for any radius r if and only if all the coefficients of the power series are equal to 0, with the exception of the first one, that is for n equals 0, which means that the entire power series must be equal to 0 with the exception of its first term, which is a constant. So your function is actually a constant. This is a powerful theorem. For example, you could, as an exercise, use the Liouville theorem to show that any polynomial with complex coefficients has at least one complex root, which is the statement of the so-called fundamental theorem of algebra, which actually implies that any polynomial not only has one complex root, but actually has a number of roots equal to its degree. Okay, but the most complicated, that there is at least one root, because then by dividing algebraically the polynomial with the usual division algorithm, then you will discover that all the other roots also exist. The tough part is to establish the existence of at least one root, and you can do that using Liouville theorem. Try, that's an interesting exercise. Another consequence of observing the connection between power series and trigonometric series is the classical maximum modulus theorem. In this case, what we need is just the first coefficient, C0, of the power series, which has this representation. That's the first coefficient of the power of the Fourier series. And also in this case, as an exercise, you can try to derive from this expression above the maximum modulus theorem, which says that if omega is an non-empty connected open set where the function f is analytic, and if the closed disk D with center A and radius R is contained in omega, then the absolute value of the function f evaluated at the center of the disk is never larger than the maximum among the absolute values that the function takes along the circle. So it is, and furthermore, the equality between the two can only occur if the function f is a constant in omega. So this means that the function f in absolute value has never a local maximum at any point inside the open set omega, which is also a behavior that is not trivial, because you can easily conceive functions of two variables in the plane which have minima, maxima. However, if you consider the absolute value of an analytic function, then neither maxima nor minima, as you can easily establish, may exist. If you apply the same kind of reasoning separately to the real and imaginary parts of the function f, which are harmonic functions from the first lesson, you will discover that the maximum modulus theorem also holds for any harmonic function. So any harmonic function cannot have interior maxima or minima. And so you get, just to make a quick incursion in electromagnetic theory, remind that, for example, TEM modes do not exist inside metallic waveguide whose cross-section is simply connected. For example, if you consider TEM modes as particular cases of transverse magnetic modes, whose eigenfunction must be equal to 0 on the boundary of the cross-section, since the eigenfunction satisfies Laplace equation, that's an harmonic function. And so we have an harmonic function whose value must be equal to 0, is equal to 0 on the boundary, okay, for TM modes. Now, for TEM modes, actually, the condition of being equal to 0 is relaxed, because it becomes the condition that the function is constant along any connected component of the boundary. So if the boundary is made of unique curve, as in a rectangular waveguide, then your function must be constant along that single curve. And the maximum modulus theorem then tells us that it must be constant everywhere. So that's a trivial function, because the electromagnetic field that you would derive from that eigenfunction would be identically 0. In a doubly connected waveguide, like, for example, the coaxial cable, you would have a cross-section with two separate boundaries, the outer circle and the inner circle. And in that case, the eigenfunction can take different values on those two circles. So it is not forced anymore by the maximum modulus theorem to be equal everywhere. And in fact, in that case, you can have a non-trivial eigenfunction, which gives you the ordinary TEM mode of the coaxial cable. So you get an alternative proof about the existence or non-existence of TEM modes by means of complex analysis. Okay, the last part of this lesson will be devoted to the extension of the Koshi theorem from the local version that we examined so far, which was applicable to convex sets, to more general sets. We will need to define what is a cycle, gamma, in the complex plane. We define a cycle, capital gamma, to be the union of closed curves. So the definition is very simple. And what you see here in the box is the statement of the Koshi theorem in its global form. Let us read it. Suppose that a function f is analytic in omega, where now omega is not constrained. That's only an open set, an arbitrary open set in the complex plane. So we don't need convexity. If gamma is a cycle in omega, so the union of a finite number of curves, that satisfies the condition that the index of the point alpha is equal to 0 with respect to omega for every alpha outside omega. Okay, so this cycle does not wind around any point outside omega, in other terms. Then what happens is that you may evaluate the function f by means of the Cauchy integral formula, as we stated it in the local form, for any z, which is in omega, but is not, of course, on gamma, which is the integration domain. And furthermore, the integral along gamma of the function f itself is equal to 0. So we are extending both the Cauchy integral formula and Koshi theorem to an arbitrary cycle, so the union of closed curves, without the assumption of convexity. What we need, however, is the assumption that this cycle gamma does not wind around points outside omega. So, as a consequence, if gamma 0 and gamma 1 are two cycles in omega with the same index with respect to any point alpha outside omega, then as a consequence of the previous statement, you may conclude easily that the integral of f with respect to gamma 0 is equal to the integral of f with respect to gamma 1. Let us illustrate this in practice. Consider, for example, this picture in which you see omega is now the blue set, the light blue set, in which you see there is a hole. So if it were the cross-section of a waveguide, that would be a doubly connected section, okay? And consider the cycle, which is the union of these two closed curves, gamma 1, which is running in a counterclockwise direction, and gamma 2, which is instead oriented in the clockwise direction, okay? Now, this cycle is entirely in omega, and it does not wind around any point, because if you consider points outside omega, then both gamma 1 and gamma 2 do not wind around them, so their index is 0. Whereas if you consider points in the hole inside, then both gamma 1 and gamma 2 wind once around those points. However, one winds in a clockwise direction, the other one in the anti-clockwise direction, so their indexes are equal to plus and minus 1 respectively. So if you consider the cycle, which is their union, the index will be the sum of the indexes, and so the index plus 1 summed with the index minus 1 gives you 0. So again, there is no winding around any point outside omega. By the global Koshi theorem, we may conclude that the integral along this cycle of the function f must be equal to 0. Okay. Note that the global Koshi theorem could not be applied separately to gamma 1 and gamma 2. That's because each of those curves winds around points in the interior. However, it can be applied to their union for the reason I have just explained you. And as a consequence, now if you reverse the direction in gamma 2 so that now both gamma 1 and gamma 2 go counterclockwise, okay, then you may conclude immediately from the previous result that the integral along gamma 1 must be equal to the integral along gamma 2. So you have a way of replacing gamma 1 with gamma 2 or vice versa without changing the value of the integral. So that's the point. The global Koshi theorem tells you under what circumstances you can change the integration domain without altering the value of the integral. The way to obtain this is to have a cycle that does not wind around points outside gamma, as in the previous slide. Okay, in the previous slide, the cycle would not wind around any point outside. So if you now reverse the direction of gamma 2, you obtain the possibility of deforming or changing the integration path from gamma 1 to gamma 2 without changing the value of the integral. Actually, I use the word deforming because it can be proved that if gamma 1 and gamma 2 can be continuously deformed one onto the other, while remaining within the region omega, then the index of gamma 1 is equal to the index of gamma 2 for any alpha not in omega, and this is equivalent to saying that their integrals are the same by the global Cauchy theorem. So one way to be sure that you don't alter the value of the integral is to make a continuous deformation of the integration domain while remaining inside the domain of analyticity. That's the point of the global Cauchy theorem. And the most important probably application of this is the so-called residue theorem. Well, residue is a word that was adapted from the French residue that was introduced by Cauchy. Residue means what remains. A function f, let's give first the definition. A function f is said to be meromorphic in an open set if there is a set, a subset A of omega, such that A, this subset, has no limit point in omega. The function f is analytic in omega with the exception of this set A, and f has a pole at each point of this set A with some principal part. Okay, the principal part is the linear combination with coefficients c sub k of the inverse monomials z minus a to minus k. The number C1 in particular among those coefficients is the most important one, and it's called the residue of the function f at the pole singularity located at A. And we will write C1 is equal to residue, of the function f, semicolon, A, which reminds us what pole are we referring to. Each pole has its own residue, and different poles will have in general different residues. It is also possible that the residue is equal to 0. That's a possibility. Now, the residue theorem tells us that if you have a meromorphic function in omega, and this function has a set of poles that we will call again A, then if gamma is a cycle in omega without the poles, which does not wind around any point in the outside of omega, then the integral of the function f along the cycle gamma divided by 2 pi j, that's equal to the sum of the residue at all the poles, each residue being multiplied by the index of the pole A with respect to gamma. So if you are able to evaluate the residues, you have a means for evaluating the integral that is on the left-hand side of this equality. And actually, this is the use of residue theorem. That's a powerful means for calculating integrals. That's because it is often easy to calculate residues, much easier than evaluating the integral on the left-hand side. And we will see some example immediately, a pair of examples that will conclude this lesson. Let me drink before. The first example is the evaluation of a real integral, which is actually an improper integral. That's the integral from minus a to plus a of the function sine of x divided by x, so the sinc function, times the exponential e to jxt with respect to t. Even though the exponential is complex, this could be split into a cosine and sine functions. And so what we would get is two real integrals, okay? But it's convenient to take this exponential, this complex exponential here, because we, as we will see now, we will be able to apply the residue theorem and therefore be able to evaluate the value of this integral in the limit when a goes to infinity. And therefore, this integral, which is an ordinary integral, if the integration limits are finite, becomes instead an improper integral, because the integrand is not integrable in the neighborhood of infinity. However, this limit exists, so this exists as an improper integral of the Cauchy type. Now, the key observation is that the integrand can be considered as a function of a complex variable just by replacing the real variable x with a complex variable z. And this, in this way, what you obtain is an integrand which is actually an entire function. That's because the exponential is entire. And because the sine function divided by z could be shown easily to be also entire, because it has a removable singularity at the origin, as you know, where its limit value is equal to 1. Now, since this is an entire function, then instead of integrating along the real axis from minus a to plus a, as in the original integral, we can deform continuously the integration path while remaining within the domain of analyticity, which is in this case the entire complex plane, and deform the original integration path to the new path indicated here in blue in this picture that we will call gamma sub a. This path is made of two straight portions from minus a to minus 1 and from plus 1 to plus a, and a half circle in the lower half plane of the complex variable z. Okay? The Cauchy global theorem guarantees us that the original integral will have the same value as the integral along this new deformed path, gamma sub a. Why deforming this path? Well, because we wish to avoid the origin. And why we wish to avoid the origin? Because we now represent the sine function as a linear combination of complex exponentials. If you do that, imagine to replace the sine function with this linear combination of complex exponentials and then split the integral, then each of the two resulting integrals would have an integrand with a pole singularity at the origin. Okay, because in this case we would have an exponential in the numerator instead of the sine function divided by z. So therefore the denominator goes to 0 at the origin, whereas the numerator does not go to 0 at the origin. So we get a pole singularity, and that's why we wish to avoid the singularity by making this circular detour, half circular detour. Now, if you define the function f sub a of s, where s is a real number, as you can see at the bottom of this slide, as the value of the integration along the half circle gamma of the exponential e to j s z divided by z, okay? In this way, it's easy to see that our original integral, the one where the sine function is, can be evaluated in terms of this new function phi in this way by evaluating the function phi sub a in t plus 1 and then subtracting phi sub a evaluated at t minus 1. Okay, that's immediate if you represent the sign in terms of complex exponentials. Okay, so what we will address now is the evaluation of this function phi. And to evaluate the integral in its definition, we will close the integration contour in two different ways. One way is the upper contour, gamma plus, which is a circle with radius a that goes from plus a in a counterclockwise direction up to minus a. The other possibility is to go through gamma minus. So now in this case, you go from plus a to minus a downwards, okay, in clockwise direction. Examine what happens, for example, when you go downstairs. So if you close the contour, what you get by the union of gamma A and gamma minus is a closed contour, inside of which your function is holomorphic. That's because the exponential divided by z has a simple pole at the origin, and the origin is outside the closed curve in the lower half plane. So by means of Koshi theorem, we can say that the integral along gamma A plus the integral along gamma minus of this exponential divided by z must be equal to 0. This is equivalent to saying that the function 1 over pi times phi a of s is equal to its evaluation along the lower circle. So it's equal to 1 over 2 pi times the integral that goes from minus pi to 0. So in this case, we are running along gamma minus, but now from minus a to plus a. And you evaluate the exponential, and the integral is evaluated with respect to the angle theta. The other possibility was to close upstairs, and in that case, what you get is a closed integration domain which wins around the pole once. So in that case, you may apply residue theorem and evaluate the integral. Since the residue is equal to 1, as you can easily establish by means of the power series representation of the exponential, then what you get is that the function 1 over pi times phi a of s is equal to 1 minus the integration performed from 0 to pi, so in the direction of the green arrow in the upper gamma plus domain, of again the exponential integrated with respect to theta. Okay, so with this result now, we can evaluate the exponential function in absolute value. Since the absolute value of the exponential function derives from the real part of the exponent e to j theta, sorry, from the imaginary part of the exponential e to j theta because of the presence of the imaginary unit j here, then the absolute value of this exponential is equal to the real exponential e to minus as sine theta. So we may conclude that because of this, the integrals over the two circles, gamma minus and gamma plus, go to infinity when a is made very large. So if you let a go to infinity, you have those two half circles that becomes larger and larger, but the integral along those half circles goes to 0. To see that, consider, for example, gamma plus. For gamma minus, it's the same. Let us try to find an upper bound for the absolute value of the integral along gamma plus. First of all, the absolute value of the integral is less or equal to the integral of the absolute value. So that's the integral of e to minus sa sine theta, which is the result I was mentioning on top of this slide. Then we can consider that the sine function is symmetric with respect to pi over 2, if you consider the graph of the sine function. So you can split this integral into two equal parts, and you can just integrate from 0 to pi over 2, and then double the result. Finally, that's the crucial step. You can observe that the sine function is convex when its argument goes from 0 to pi over 2, which means that its graph is always above the secant that goes from the origin to this endpoint here. So therefore, the sine of theta is always greater than or equal to this green straight line, which is 2 over pi times theta. That's the so-called Jordan's inequality. Because of the minus sign in this exponential here, then if you replace the sign with the secant, you obtain something that is larger. So if you do that, you have this further inequality, but now the integral can be evaluated because that's now an elementary integral. And the result is the one that you can find here in this last part of the calculation, where now you can let a go to infinity, and you will discover that this thing goes to 0. So because of these inequalities, we will conclude that the integral along gamma plus must go to 0 as the radius of the circle goes to infinity. But if this is true, then we find that the contribution of the integrals along the circles is 0 in the limit. So in the limit, when a goes to infinity, the function phi has just two values. That's equal to pi when when its argument is positive, and it unit step function multiplied by pi. And finally, coming back to our original integral, I sub a, since I sub a is the difference of the function phi sub a evaluated once at t plus 1 and another time at t minus 1, we are able to find the final result, that is the integral from minus infinity to plus infinity of the sinc function times the complex exponential e to j xt, which is nothing but the Fourier transform of the sinc function, that's equal to a constant equal to pi inside the interval between -1 and +1 and 0 outside. So we have found that what we know from Fourier analysis, that the Fourier transform of the sinc function is the rect function times pi. Okay. Note that it would have been much more complicated, probably impossible to show that without using complex analysis. That's why many times going into the complex plane, even though it may seem to complicate things, actually it makes things simpler, because if you stick to the real axis, sometimes it's impossible to evaluate the integrals. Okay. Another example, and then we conclude, concerns the so-called Fresnel integrals, which are very useful in many problems of electromagnetic scattering. Consider those, again, two real improper integrals. One is the integral from 0 to a of the cosine of t squared, and again in the limit where a goes to infinity. Let's call this limit I sub c, and something similar with the sine function. The limit will be called I sub s. Those two numbers is what we wish to evaluate, and those are the limit values of two functions that are known as Fresnel integrals, c of x, in which now x is the upper integration limit of the same integral with the cosine, and s of x, in which x is the upper integration limit of the function of the integral in which you can see there is the sine. We will again make use of the Koshi theorem. In this case, we will apply it to the entire function e to minus z squared, which will be integrated along this closed contour, in which we have the union of three curves, gamma 1, which is a straight line that goes from the origin to the point r along the real axis. Then we go along a circle with radius r, from the real axis up to the bisectrix of the first quadrant, where the argument of the complex numbers is equal to pi over 4. And then we come back to the origin through this bisectrix, and that's gamma 3. Okay. In this picture, you can see also the parametric representations of the three parts of this closed contour. Gamma 1 is given simply by z equal to t, where the parameter t goes from 0 to r. In gamma 2, the circular part, we have the polar representation z equal r, the radius, times e to jt, where t now is an angle that goes from 0 to pi over 4. And finally, we have the last straight line in which you have z equal to t times the complex number e to j pi over 4 that give you the right argument. Okay, now in this case, t goes from 0 to, t goes from 1 to, from r, which is the starting point, to 0. Okay. Okay, the integral along the circular arc can be shown to be negligible in the limit when the radius goes to infinity, and the reasoning is exactly the same as before. I will show you it again for clarity. The absolute value of the contribution of gamma 2 can be estimated through an upper bound by integrating the absolute value of the exponential. Now, the absolute value of the exponential, if you perform the calculation, which is trivial, is given by the real exponential e to minus r squared cosine of 2t. This must be integrated from 0 to pi over 4, and there is also this radius that pops out from the differential and that has been taken outside the integral. But now, the cosine function is convex when its argument goes from 0 to pi over 2. As you can see again from the graph, you can see that the cosine in blue is always above the second, which is 1 minus 2 pi times theta. So if you let theta now be equal to 2t times t, this form of, again, Jordan's inequality lets you find an upper bound for the absolute value of your integral, in which now you integrate something that can be integrated analytically, and the result again goes to 0 when the radius r goes to infinity. So you can neglect the contribution of gamma 2 when r goes to infinity, and you will remain with the integral along gamma 1 and the integral along gamma 3. But since the Cauchy theorem tells you that the sum of those two integrals must be equal to 0 because of the analyticity of the integrand inside, then what we have is that the integral along gamma 1 is equal and opposite to the integral along gamma 3. Now, the integral along gamma 1 is the integral from 0 to r of e to minus t squared. If you let the upper integration limit go to infinity, you end up with the standard Gaussian integral, which we know is equal to the square root of pi divided by 2. So that's a standard result in real analysis. On the other hand, the integral along the bisectrix gamma 3, if you let z be equal to t times e to j pi over 4, the parametric representation of the bisectrix, and the same you do in the differential, by performing the algebra, you end up with this integral where you go from 0 to r, e to minus jt t squared with respect to t. And again, if you let r tend to infinity and you split the real and imaginary parts of that integral, you end up finding IC and minus IS, which are what we wish to evaluate, respectively the integral of cosine t squared and the integral of sine t squared. So now you put all the pieces together, and you have that the integral along gamma 1, this constant here, minus the integral along gamma 3, which is a linear combination of IC and IS, that must be equal to 0. Now, what we need to finish is to separate the real and imaginary part in this equality to obtain a 2 by 2 system in 2 by 2 real unknowns, from which you can immediately find IC and IS. It turns out that they are equal, and they are equal to the square root of pi over 8. Okay, so that's another example in which, by using Koshi Theorem, in this case we did not even use the Residue Theorem. Koshi Theorem was enough to find the value of a real integral that would be otherwise impossible to evaluate in a different way. That was my last slide for today. Again, stuff you can find much more than these in these books and in many others. With this lesson, I hope I have given you the necessary background for understanding what I will be telling you in the next weeks. And in particular, next week, I will devote our attention to asymptotics, so asymptotic analysis. Okay, I will stop here for today. So thank you again for your attention. If there are questions now or whenever, feel free to ask or to write me by email.
Thank you very much.
Otherwise, thank you for being here and see you next Tuesday. I will post the slides and recordings in 1 hour or so, I think. Thank you.
Thank you,
bye
Professor.
Bye.
Have a nice day.
Thank you.
You too.
Bye-bye.
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 Bye-bye.